All right, it should come now to no surprise that we are going to find a confidence interval now using the t-distribution. Notice that the confidence interval formulas are pretty much the same. The only difference is we're throwing an S in here. So the idea now is when we have small samples, that is n less than 30, sigma unknown, we should check and make sure that this normal assumption or approximate normality, you really should check, especially when you have the data, to assess that you do have at least approximate normality. By approximate, I'm meaning, remember when do you guys remember how to check for normality? How do we check for normality? We make a normal probability. Yeah, you two working together. Really good. Yes, we use a normal probability plot, and if it's linear, we can determine and assess normality. If there's a little bit of deviation in the tails due to the thickness of the t-distribution tails, formally they kind of say the robustness of the t-distribution, it's okay if you've got a little wiggle room there at the tail ends. Approximate normality is sufficient as well. So you really should, if you have the data at hand with a small sample set, check for normality. Because if you don't have the normality assumption, or if you don't have the normality, you might be off. And remember, the central limit theorem works for large populations, so you really should. But a lot of times we don't give you the data, but just in case you ever do. So let's compute one of these real quick and see where this is going to lead us to. So because of the cardiac deaths appear to increase after heavy snowfalls, a study was designed to compare cardiac demands of snow shoveling to those using an electric snow thrower. 10 subjects cleared tracts of snow using both methods, and their maximum heart rates were recorded using both activities. The following results were obtained for the snow shoveling portion of the experiment. So N is 10, the sample mean is 175, and S is 15. So we would like to use a 95% confidence interval. Did I say we would like to compute a 95% confidence interval. Now, before we start crunching these numbers, we need to make a few observations. Number one, I am observing that the sample size is 10. Since the sample size is 10, I know I'm going to have to use a t-distribution. Okay? So this is how you're going to have to decide which kind of a confidence interval you're going to construct. All the other previous examples we were working with all had sample size bigger than 30. Now notice that these ones are smaller than 30. And notice, secondly, we have our good old friend over here, S. So there are two key pieces of information that tells you that you need to use the t-distribution. So before you start crunching out these intervals, you have to figure out which one you're going to use first. Okay? That was a question. Are we okay? Does that make sense? You have to figure out which one to use, which types of intervals. T-scores or Z-scores, T-intervals or Z-intervals. So in this case, we know we're going to use the T. So we need to find our T-score. So let's just note that alpha is equal to 1 minus 0.95, which is equal to 0.05. Alpha over 2 then is 0.05 divided by 2, which is 0.025. And our degrees of freedom is going to equal to what? 9. Very good. So looking up the .025 column, and then going over to the degrees of freedom row of 9, we should have a T alpha over 2 is going to equal to what? 2.262. I'm sorry, was that everybody that said that? I know Bill and Randy did. All right, so now we can form our confidence interval. So we're going to have what? 175 plus or minus our t-score 2.262 times s 15 over the square root of 10. The n minus 1 only comes for the degrees of freedom. Yeah. So here we get 175 minus 2.262 times 15 over the square root of 10. So we come up with about 164. Change the minus to a plus, so we get about 186. Just a tad bit of rounding. So we get 164 and 186. So this is our 95% confidence interval.